Hello, this is the course on econometric modeling. I welcome you to module 3. The previous two modules have discussed the basics of econometrics, how it is defined, what are its types, the applications and the steps in formulation of econometric modeling. Now, the third module basically deals with review of basic concepts. The fourth module also deals with the same thing. So, first we begin with module 3, which takes up review of basic concepts. So, some statistical concepts primarily which are very useful in the field of econometrics and will be repeatedly applied or used in the field of econometrics. So, first of all we define random variables. A random variable is any variable whose value cannot be predicted exactly. So, first of all variable implies something which values keep on varying, and when we add some randomness to it, then it basically adds certain uncertainties to it. An uncertain event can never be predicted with 100% accuracy. Consequently, at a random variable can never be predicted exactly. Random variables are of two types. First of all, discrete random variable. They are the one that has a specific set of possible values. An example is the total score when two dice are thrown. So, these specific values could be 2 to anything between 12, but the numbers are always whole numbers like 2, 3, 4, 5, 6, 7 and so on. On the other hand, a continuous random variable can take any one of a continuous range of values, for example, daily average temperature of a place. It can be also some economic numbers or numbers related or numbers from the field of economics. For example, if we calculate growth values of any series, for example, if I consider GDP, then GDP is calculated, growth in GDP is calculated as GDP at time t plus 1 minus GDP at time t divided by GDP at time t, say multiplied by 100. In that case, this calculation can yield any number. So, we generally say that the economy has grown at a rate of 7%, nearly 7% or 6%, nearly 6% and so on. But the actual values can be like 7.3215 or it can be 5.4901 and so on. So, since these are calculations, they can take any value, and that is how we do not call them discrete random variables. Then we differentiate between population and expected value. The set of all possible values of a random variable is described as the population. For example, the population for the total score when two dice are thrown is the set of numbers from 2 to 12. See, we are throwing two dice simultaneously. So, the lowest value that each one can take is 1. So, 1 plus 1 makes it 2. The maximum value each one can take is 6. So, 6 plus 6 12, and it can be anything in between, that is one dice has come up with 1 and the other dice has come up with 2. So, it adds up to 3 and so on. So, the population, that is the set of all possible numbers obtained by throwing two dice, are between 2 to 12. It contains all possible values. So, that is population. The expected value of a discrete random variable is the weighted average of all its possible values, taking the probability of each outcome as its weight. So, I will show you some examples, but before that we will define it, that in mathematical terms, if x is a random variable, then that takes n particular values like x1, x2 to xn, and the probability of xi is pi, then the expected value of x is calculated following this formula, where expected value of x is x1 multiplied by p1, x2 multiplied by p2 and so on, thus xn multiplied by pn, and finally we come up with this sum. So, what is happening here is that expected value is actually the sum of weighted summation of individual observation. So, when I say that and the probability of xi is pi, then this I is anything from 1 to n, right. So, xi is occurring with a probability of pi, which implies that x1 is occurring with a probability of p1, x2 is occurring with a probability of p2 and so on. Then we discuss the concept of population mean. The expected value of a random variable is frequently described as its population mean and it is often denoted by mu. So, expected value is actually equivalent to the mean of the population observations and it is denoted by mu. So, here is the example. We continue with the example of the two dice and the possible outcomes. So, what are the possible outcomes? As I have explained earlier that when we simultaneously throw two dice, then the minimum values their sum can take is 2, and similarly, so there can be the sum can be 3. Now, you can see that the possibility of 2 coming up is 1 out of all 36 possibilities, right. Similarly, 3 can come up only twice. So, that the two instances are, first of all, first dice take value 1 and the second dice take value 2. Alternatively, the first dice take value 2 and the second dice takes the value 1. So, there are two instances when it can be 3, and similarly we can find out that there are 4 instances, 3 instances where the sum can be 4, there are 4 instances where the sum can be 5 and so on. So, the way we calculate probability of an event occurring is the possibility, the number of times it can occur divided by the total number of times different values of the population takes up. So, 36 is the total number and the possibility that the sum will be 2 is only 1. So, 1 upon 36 gives us the probability of the sum being 2 and so on. Finally, in the last column what we are doing, which is equivalent to x1 p1, we are multiplying x with p. So, 2 multiplied by 1 by 36 and so on, and finally, this gives us our expected value of x, which is summation xi pi. So, we sum all this together and arrive at a value of 252 by 36, which is equivalent to 7. So, this tells us that the population mean or the expected value of x is 7 for this particular example. Now, we talk about independence of random variables. Two random variables x and y are said to be independent if expected value of g x multiplied by h y is equal to expected value of g x multiplied by expected value of h y for any functions g x and h y. So, g x and h y here refers to any general functional form of two random variables x and y. So, g x basically refers to some functional form of x. It can be simply the values of x, it can be x square, it can be x cube, it can be logarithm of x and so on. Similarly, for h y, for any functional form of y, we refer to it as h y, a general functional form. So, what independence implies is that expected value of the multiplication of the two functional forms of the two variables is equal to the multiplication of expected values of the two functional forms. Independence implies as an important special case that expected value of x y is expected value of x into expected value of y. So, basically here in this case from this generic functional form we are coming to a specific functional form which is only x. So, here g x is equal to x, and that is how expected value of x y is equal to expected value of x multiplied by expected value of y. Now, this is actually a very important thing to remember. Why this independence of random variables implies it so is actually outside the purview of the course. I am just introducing you these concepts which we are going to use in the subsequent modules again and again. Coming to population variance and standard deviation, population variance and standard deviations are two useful measures of the dispersion of a variable's probability distribution. So, a probability distribution is often a reflection of what is the distribution of the data generated with certain level of probability. Now, how the data generated or how the distribution is dispersed is actually reflected in terms of population variance and standard deviation. The population variance of a variable x is obtained as expected value of x minus mu square. So, you see that whenever we are calculating variance, suppose we denote it by variance of x, then that is actually denoted by sigma square x. Sigma square is the common notation for variance. If we are obtain it for x, then we have a subscript x. If we are obtaining for a variable y, we can add a subscript y and so on. And this variance of x is when expanded in terms of expected value, it takes this functional form. So, expected value of x minus mu whole square is variance of x. Now, when we further expand it following the formula of expected value, then it would be x1 minus mu square multiplied by the probability of x1, x2 minus mu whole square again multiplied by the probability of x2 taking place and so on. And that is how we have this expression, and when it is summed up, then we have this summation notation which says that summation I equals 1 to n xi minus mu whole square multiplied by pi. Just to recap that mu is the population mean of the variable x here. So, this is how population variance is calculated, and the population standard deviation of a variable is the square root of its variance and is denoted as sigma x, right. So, sigma square x root over gives us the population standard deviation which is sigma x. Now, we take up another example. If you recollect, then the population mean was calculated to be 7. So, mu is equal to 7 and the standard deviation is calculated from here which is 2.41, where the variance is actually 5.83. Now, you can see that continuing with that example of the sum of two dice when they are thrown together, then what are the outcomes? We have values of x taking values of x from 2 to 12 and their associated probabilities are also mentioned here. Now, what I am doing is that this is the x minus mu column. So, 2 minus 7 is minus 5, 3 minus 7 is minus 4 and so on. Then we have x minus mu whole square. So, I am simply taking the square of this column. So, minus 5 square is 25, minus 4 square is 16 and so on. Then this column is multiplied by the probability values. So, this is x minus mu square multiplied by p, summing them up I arrive at 5.83 which is the population variance, and square root of 5.83 is 2.41 which is the population standard deviation. So, this is how we calculate population variance and population standard deviation. As you can understand that this ideally tries to tell us that how much individual values have deviated on average from the mean of the series. So, this is the deviation. Now, if I add the deviation simply, you would see that we would arrive at a 0. So, most often the deviations of individual values from the mean, when summed up, they would come to 0. Specifically, if we have a nice looking distribution, that is everything is centered around the mean, then the deviations would all add up to 0, because the negative and the positive, they would cancel out, right. So, in order to avoid this problem, we take first the square root, then multiply it with the probabilities and sum up, and when we take the square root, then we actually somehow take care of this square root thing. So, as a result of which, standard deviation could tell us roughly what is on average the deviation of individual values from its mean, right. Now, we talk about the components of a random variable. Instead of regarding a random variable as a single entity, it is often possible and convenient to break it down into fixed component and a pure random component. The fixed component always being the population mean. So, basically we are here trying to bring in some kind of uncertainty, because as I told you in the beginning that random variables has certain randomness in them, and randomness is difficult to predict. So, if it is completely random, which implies there are too much of uncertainty, then it is very difficult to predict. In order to come up with some level of certainty and predictive ability, we can basically introduce this certainty by dividing a random variable into two components. The first component is a fixed one and the second one is completely random. So, the fixed component most often is actually the mean of the series. So, what we are doing here is that if x is actually the random variable, then mu being the mean of this random variable, this is sort of non-random component, which you also called a deterministic component, and u is a purely random component. Okay. So, if x is a random variable and mu is its population mean, one may make the following decomposition, where x is equal to mu plus u, where u is pure random component known as the disturbance term in regression analysis. U actually stands here for unobserved component. So, u stands for unobserved. This unobserved component is actually the component which has certain uncertainties associated with it and difficult to predict. Now, we talk about mean and variance of u. Basically, the regression analysis put a lot of importance to this concept of u, because the thing is that if this u component is not here, which implies that there is no randomness to it, and if there is no randomness to it, then we do not need actually statistics and econometrics. Everything would be deterministic, everything can be predicted with 100% certainty, and that can be done using mathematics, simple or complex, whatever. So, u actually plays a very important role. When we will get into the regression analysis, you would see that all the assumptions actually revolved around u, that how this unobserved component should behave, what kind of behavior is desirable, and on that basis the quality of our regression results actually can be determined, or on that the quality of the regression analysis depends to a large extent. So, u plays a very important role, mu has actually nothing to do, because it is a fixed component. So, we talk about different features and characteristics of u. We begin with the mean and variance of u. So, since u equals x minus mu, expected value of u I that is, here we are considering the population mean of the unobserved component, right. So, what we are doing is that ui is replaced with xi minus mu, and mu is actually a non-random component. So, when we further break up this expected expression, we have expected value of xi minus expected value of mu. Now, since mu is non-random, it does not have any expected value, it is a fixed number, it is a constant term, right, like 2, 3, 4, any discrete number or any number like 2.53, 2.64, whatever be it. So, a number does not have any variations associated with it, any probability associated with it. So, expected values or mean values are actually the same. The mean of 2 is 2, the mean of 4 is 2, maybe it does not make any sense altogether. So, this actually remains mu, while we know that expected value of xi is mu. So, mu minus mu becomes 0. So, expected value of the unobserved component is 0. Now, here in this context, I will take you to the previous example that we had taken, where you can see that we also argued that this is x minus mu, and the expected value of this x minus mu, or rather here the sum actually appears to be 0. If we calculate the expected values, you would find that it turns out to be 0. So, the thing is that the unobserved component or the error term most often tends to have 0 mean. Then we talk about further, since all the variations in x is due to u, the population variance of x is also equal to the population variance of u. What I am trying to tell here is that population variance of x is actually expected value of x minus mu square. Mu does not have any variation in it. So, expected value of mu, or rather here the variations in mu is actually 0. So, what I am left with is this is replaced with u. So, expected value of u square, and that is equal to sigma u square. Now, how I am coming at it? So, expected value of sigma u square is actually expected value of u minus the mean of u. Now, we have already seen the mean of u is actually 0. So, mean of u is 0. So, here I am left with expected value of u square, right, and expected value of u square is actually variance of u. That is what I had explained earlier only, right. So, this is a common practice that if I write variance of x, then this is expected value of x minus mean of x whole square, right. So, if the mean of x is 0, then this becomes expected value of x square. So, the same thing is happening here. So, this is variance of u, and that is how this is variance of u. Now, we talk about estimators. What is the concept of estimator? How are they different from estimates? So far we have assumed that we have exact information about the random variable under discussion. In particular, that we know the probability distribution in the case of a discrete random variable or the probability density function in the case of a continuous random variable. With this information, it is possible to work out the population mean and variance and any other population characteristics in which we might be interested. So, we are so far dealing with population, right, but the problem is that most often population is not available to us, population is not observable to us. For example, if I want to find out the impact of parental education on a child's education. So, for that I may need to collect data from some number of individuals. So, if I want to consider the population, suppose my study focuses on India, this means I must consider all the parents residing in India or those who are residents of India and their children. Suppose I also specify the children's education. So, I begin with children's education. Suppose I consider a individual and I try to find out whether that individual has completed 10th standard or not. So, the education criteria or the education levels could be measured as whether someone has completed 10th standard or not, then whether someone has completed 12th standard or not, then further graduation, post graduation, professional education and so on. So, I can have several criteria for child's education, and for parental education I will then note down that the child has so and so education and his or her parents have this education. So, father's education, mother's education. I am just simply talking about the problem with population. It is so difficult for any individual to collect data from all the parents and all the children who are residents of India or who are residing in India. So, even if my population is confined to India, this actually becomes a Herculean task. So, what we try to do is that we take up a sample. So, this is an example where we are actually not able to work with the population. Population is not available to us. The example of dice was pretty simple, where we could work with population, but most often it is not possible to work with population. So, what do we do in that case? In practice, except for artificially simple random variables such as the number of thrown dice, we do not know the exact probability distribution or density function, because we do not have the population observed most often. So, it follows that we do not know the population mean or variance. However, we would like to obtain an estimate of them or some other population characteristic. This is done by taking a sample of n observations and derive an estimate of the population characteristic using some appropriate formula. This formula is technically known as an estimator, and the number obtained is known as the estimate. So, estimators are the formula which are giving us sample estimates of the population parameters. Population is not available, I have taken a sample, I am estimating the population parameters using the sample. So, the formula used to estimate the population parameters is known as estimators, and what we obtain from the sample as the estimates of the population parameters are known as estimate. The estimator is a general rule or formula, whereas the estimate is a specific number that will vary from sample to sample. Estimator of the population mean is mu, while estimator of the population mean is mu. So, this is basically obtained from sample. So, this is sample mean, which estimates the population mean, and we refer to it or denote it by x bar, where these xi's are drawn from a sample. The sample consists of n observations, right. Okay. Estimator of the population variance in a similar fashion is denoted by small s square, where we have xi minus x bar whole square summing up from I equal to 1 to n, and then dividing it by 1 by n minus 1 or dividing it by n minus 1. Now, why this is n minus 1 and not n, that we will pick up in a or we will take up in a later module. For the time being, we just note down this formula that 1 by n minus 1 multiplied by summation I equals 1 to n xi minus x bar whole square is an unbiased estimator of the population variance. So, this is an unbiased estimator. Estimators are random variables. It is a special case of random variables because it is a combination of the values of x in a sample, and since x is a random variable, a combination of a set of its values must also be a random variable. What it tries to tell us is that I have taken a sample of say n individuals or say 100 individuals, right. I continue with my previous proposition or problem that I am interested in finding out the impact of parental education on child education. So, first of all I have picked up 100 children and their parents. So, 100 mothers, 100 fathers say. So, I have roughly 200 parents and 100 children. Now, if I choose a different sample or someone picks up a different sample, so that sample could be another 100 children and another set of parents. So, this makes basically estimators a random variable because I can have different estimates of the population mean and variance using different samples, right. So, that is why it is said that an estimator is actually we are working with a combination of the values of x in a sample, and since x is a random variable, a combination of a set of its values must also be a random variable. So, this is what is the first part of introduction or review of the basic concepts. These are the books that I have followed in order to come up or present these ideas. I will next continue with the review of basic concepts in the next module as well. Thank you.